the probability of error of quadrature phase shift key. If we briefly outline what is the QPSK structure, so that we understand the receiver section of the QPSK, then we will easily understand about the probability of error of a QPSK receiver. Normally, in QPSK, quadrature phase shift keying, there are 4 levels. Each level we modulate as a symbol. The symbol is bit symbol. There are 4 levels. For every 2-bit combination, you will get 4 levels. So because these are 4 levels, there are 4 phases. Those 360 degrees divided into equally 4 phases, we can divide pi by 2 or 90 degrees or pi by 2. We can have the phase difference between each symbol pi by 2. So that is why 0, pi by 2, pi 3 pi by 2, or combination of any phases with a difference of pi by 2. Now these the data, a combination of 2 bits if you take, for every combination of 2 bits, odd and the even bit, Okay, so we separate these 2 bits into different channels. One is in phase channel, other is a quadrature phase channel. The 2 channels. So in this symbol, we separate into 2-bit combination. So each bit like a BPSK again. We transmit. Then both we combine. So that is how odd and even bit to modulate in case of 4 levels with a 90-degree phase shift. Okay, so this is where the combination of the phi difference cos 2 pi, okay, plus theta, where theta phase is 2i minus 1 pi by 4. For I equal to, see here there are I equal to 1, 2 minus 1 pi by 4, I equal to 2, 4 minus 1, 3 pi by 4, 5 pi by 4, 7 pi by 4. So that is what phase difference pi by 2. And odd, even. So these are all odd bits. Odd bits are separated 1, 1, 0, 1, 0. Odd bits. Even bits are separated 0, 1, 0, 0, 0. So in every symbol, odd and even bits are separated. So this is one channel, I channel. Okay. This is another channel, quadrature channel. We modulate each one as BPSK. If at all we expand the expression of previous one, cos A plus B, cos A cos B minus sin A sin B. We express. Okay. And here the energy of a symbol is E. Energy of the symbol is E. And energy of a symbol is A, 2-bit combination to 2E. Energy of symbol, the time duration of the symbol T equal to 2-bit duration, 2-bit duration, 2B. So anyway, combination of this cos A cos B minus sin A sin B, this is what expressed phi 1 of T, phi 2 of T. Both are orthogonal to each other. Root 2 by T cos 2 pi of ct, root 2 by T sin 2 pi of ct, both are orthogonal to each other. So this is the signal vector representation where phi 1 and phi 2 for a bit duration of 0 to 3, symbol duration. Okay, consider the coefficients. So this is where SI1 phi 1 of t plus SI2 phi 2 of t is SI of t is the signal representation. These are the coefficients of this. This is the coefficient of this. So SI1, SI2 multiplying with phi 1 and phi 2. So now there are two channels. This is one channel. This is another channel. SI1 multiplied with phi 1, SI2 multiplied with phi 2. So that is where the block diagram of the transmitter dividing, separating odd and even bit as a symbol here. The data sequence coming over here, the sequence of like this, separating odd and even, polar non-return to 0 level encoder. This encoder is getting root EB minus root EB like that. And demultiplexer is separating odd and even. Demultiplexer is separating 2 bits as a single bits in each channel. Odd SI1 amplitude root EB or minus root EB based on binary 1 and binary 0 multiplied with phi 1 of t, and this is I channel, this is I channel, and even bit multiplied, that is SI2 with based on binary 1 and binary 0 root EB or minus root EB multiplied with phi 2. This is Q channel, quadrature channel. So both are summing to, this is SI of t, both are added, and that is the output of the QPSK. Okay. So anyway, this is transmitted. We are interested in receiver because to estimate the probability of error, and the receiver again 2 correlators required. 2 correlators. In a I channel correlator, this is I channel correlator, this is a quadrature channel correlator. Each correlator has a BPSK, a multiplier and integrator, and multiplier and integrator. Phi 1 of t integrator 0 to t, phi 2 of t integrator 0 to t. And the correlator output of each as BPSK, this is x1, this is where x of t phi 1 of t dt, this is where x of t. Okay, we will get the coefficient SI1 as equivalent to plus whatever the additional noise that is being separated. This is SI1 into phi 1 of t. You will get plus or minus root e by 2. That is nothing but root EB. So this is where root e by 2 means plus or minus root EB plus noise. Similarly, in this case, minus or plus the second channel. So here we are getting the decision making of 0, threshold 0, above 0, binary 1, below 0, binary 0 as per our assumption. Okay, if your assumption is reversed, the decision is also to be reversed. Whatever the assumption you made at the beginning, the same way the decision making also to be followed. So now getting 2 bits separately, so that you will get a symbol here by combining, by multiplexing, you will get the symbol here. So this is where at each phases root e by 2 means EB, root EB minus root EB minus root EB minus root EB. So for 0, 0 minus root EB minus root EB. For 1, 0 root EB minus root EB. 0, 1 minus root EB plus root EB. 1, 1, root EB plus root EB. So E by 2 means root EB, EB. Okay. So these are the constellation. So at 5 by 2 phase difference. So this is phi 1 and phi 2. This is 1, 0. Root E by 2. This is root EB. So this is where. So this is root EB. This is minus root EB. So root EB. This is also minus root EB. This is plus root EB. So root EB minus root EB. Root EB plus root EB. Minus root EB plus root EB. Minus root EB minus root EB. That is why it's 0, 0, 0, 1. So the distance between these two, Euclidean distance AIK is 2 root EB. 2 root EB. Okay. Now the probability of error getting either binary 1 or binary 0, here, this is what the phase shift 90 degrees adjacent channels, adjacent bits, and 180 degrees between two bits diagonal. 1, 1, 0, 0, 180 degrees, 2 bits change. 1, 1, 0, 1, 1 bit change, 90 degrees, like that. Okay. Now, the probability of error in each BPSK, two BPSK channels are lower and upper channel, lower and upper and lower channel. Okay. Now, as we have seen in BPSK, the probability of error B dash, that is what BPSK. Okay, this is what PD. Of complementary error function of complementary error function of dik by 2, dik by 2 root n naught. This is d12. Or dik by 2 is the dik. What is dik? 2 root EB. Okay, 2 root EB. What is EB? E by 2. Okay, E by 2. So that is what this is taken as off complementary error function of either root E by 2 n naught. Okay, E by 2 is the root EB. So root EB by n naught. BPSK, in BPSK, that is where off complementary error function of root EB by n naught we derived. In terms of dik by 2 root n naught, or in terms of root EB by n naught, or EB as E by 2, root E by 2 n naught. So that is how each channel equivalent to BPSK, the probability of error, okay, of probability of error of BPSK, okay, of BPSK that can be taken as, because there are two channels, upper and lower channels, upper and lower channel. This is I channel and this is Q channel in VPSK. The combination, the average probability, we can take it as, okay, correct probability is 1 minus probability of error of BPSK. In both the channels, in each case, BPSK. Okay. So total probability, correct probability is PC of QPSK is multiplication of this is what square. This is what 1 minus P dash square. Okay, this is what correct probability of QPSK. Now, what is error probability? Again, 1 minus error probability of QPSK is 1 minus PC QPSK. 1 minus correct probability. So, error probability is 1 minus correct probability. Okay. And now that is what 1 minus PC. So, this is where you can take it as expanding. Okay. This is where 1 minus 1 plus P dash square minus 2P dash. This is where PPSK. 1 P dash square. This is what PPSK. Okay. And this is gets cancelled. Okay. P dash square minus 2P dash. Okay. 2P dash. 1 minus PC is P dash square minus 2P dash. So here, yeah, 1 minus PC. So, yeah, which is equal to 2P dash minus P dash square. So, 2P means twice 2 into half complementary error function of root EB by 2n0 minus square half complementary error function of whole square 1 by 4. So, this is where 2 into half complementary error function of root EB by 2n0 minus half complementary error function of root 2 by 2n0 square. So this is what 4. Now this is squared complementary error function. This is what small complementary error function, which is decreasing function, squared function, small value, squared small value is again small. This can be treated as negligible, and approximately this is taken complementary error function of root E by 2n0. Okay, this is what the probability of error. Okay, complementary error function of QPSK. So this is where complementary that the probability of error of QPSK is complementary error function of root EB by 2n0. See, this is where double of the BPSK. Half complementary error function of BPSK is root EB by n0 is BPSK. So double that of QPSK because there are 2 bits in QPSK. So the same thing can be referred probability of error as a QPSK, that is what as a symbol complementary error function of E by 2 becomes root EB, that EB, so that root EB by n0 is double the PPSK value. So if you want to estimate for bit, because this is for symbol, this is 2 bits. Per bit, again half. half of that symbol, right? So then half complementary function of root EVM, which is same as BPSK. So the probability of error is of QPSK, okay, is same as BPSK per bit, per symbol double, per symbol. So if you take bitwise in BPSK or QPSK, bitwise probability of error is same as BPSK, but symbol wise probability of error of QPSK of 2-bit symbol is the double the probability of error of BPSK. That is what the probability of error of QPSK. So because 2 bits are involved in QPSK, getting an error of 2 bits, getting an error of 112,002 bits, so it's less probable because it's more diagonal distance than adjacent bit getting 1 bit error instead of 1 as 0 1 bit error. So bitwise probability of error is same as symbol wise probability error is double of BPSK. So that is what about the QPSK.